Today what I want to look at is the law of cosines. This is our other rule. We've looked at the law of sines. And I actually want to derive the law of cosines with you. Okay? Now we have to kind of set it up here. But we've been using, triangle ABC, where you have A, B, C, and then the side A is across from angle A, side C across from angle C, and side B across from angle B. Okay, so you'll notice here that's how I have this set up, but I'm using coordinates. And this is actually something you may have done a little bit if you took geometry here, using coordinates to prove things. And I just want to show you the setup of this situation so that you can understand how we're going to prove this. All right. First of all, I put my point C at the origin, and then I made this side here have a length of A. All right, and I made it horizontal, so side BC is horizontal. So that means that point B is at the coordinates A0. All right, does that make sense? All right, so I don't know how long this side here is from A to C, but I'm labeling it B because it's across from what's going to be angle B. And since this bottom side is A, then this top point here is going to be point A. And then this side between A and B we're going to call length C. All right, now notice we don't have any numbers in here. We're doing it in general because this is going to be a proof. Okay? Now, the other thing here, notice I want to find coordinates for A in terms of what I know. So you'll notice this X is the X coordinate of A. And the Y here is the Y coordinate of A. All right? So to find this X coordinate of A, I'm going to try to adjust this here. To find the X coordinate of A, I'm going to use a little bit of right triangle trig. All right? Looking at angle C, X is the adjacent and B would be the hypotenuse. So that means that the cosine of angle C is going to equal X over B. All right? I'm looking at this right triangle here because I want to find these coordinates of A. All right, now you can see here, if X is the X coordinate of A, I could solve for X by multiplying by B, and I get B times the cosine of angle C. Does that make sense? Okay. Now I'm going to do a similar thing here with Y, except instead of cosine, I have to use the sine of angle C, and that's going to be Y over B, because Y is the opposite, B would be the hypotenuse. So now I know that if I multiply both sides by B, Y equals B times the sine of angle C. All right, so that's how I get these coordinates here, B cosine of C and B times the sine of C. Okay? Now, this is a relatively sophisticated proof. Figuring out how to set up this situation would really be one of the hardest parts of proving the law of cosines, okay? But again, just like with our law of sines, where we had to solve for the height and then do all this other stuff, and then someone eventually recognized, hey, there's a pattern here. That's how something like this would have been figured out. Someone would have been working with triangles and they found that they were having to drop this height every time and figure out what the lengths were and be doing the same process over and over again until finally they decided to try it with variables instead of numbers and see if they could come up with a formula. All right? Now, you'll notice here we're going to prove this by the Pythagorean theorem. Okay? And in order to do that, I'm actually not going to use the right triangle on the left that I got the coordinates from, because I want to involve side C okay, and also side A, along with my angle C and my side B. All right, so what I'm going to do here is I'm going to use this triangle on the right, okay? Now watch this. We see that Y is one of the sides of that triangle. So this leg, this vertical leg here, equals B times the sine of angle C, right? And then the bottom here, we know the whole length of this is A, and we know this side over here is what X is. It's B times the cosine of C. So how long would this be? Very good. It's going to be A, the whole thing, minus the left side. So minus B times the cosine of angle C. And this is the triangle we're going to use the Pythagorean theorem with. And that's how we get our equation here. A minus B cosine of C squared plus B times the sine of C squared equals C squared. Okay? So, it's just a leg squared plus a leg squared equals the hypotenuse squared. All right, any questions so far? All right, now check this out. Okay? Here's where the algebra comes in, and we're going to end up at our law of cosines. Okay? Obviously, since it's called the law of cosines, we're going to want to get rid of that sign eventually. Okay? So, let's see how we'll do this. First of all, I'm going to FOIL. Okay? I'll have an a squared minus 2ab cosine of c. Okay, we're going to have a times a negative b cosine c, and then another a times a negative b cosine c. All right, plus b squared cosine squared of c. All right, that's just this whole thing FOIL. Then here we have plus a b squared sine of c. Squared. Thanks. Okay. Okay. So we FOILed this one. This was a monomial, so there was nothing to FOIL. We just brought the square into the b and to the sine. Okay? Now, does anyone see something that we could do here on the left side?
We can change the sign to 1 minus cosine.
We could change the sine squared to a 1 minus cosine squared. What were you guys saying?
I was going to say the same thing.
Okay.
You do a squared with b squared equals 1. I mean equals c squared, but that would not do it all. Never mind.
Yeah, and in this case, a squared plus b squared doesn't equal c squared. Because it wasn't a right triangle to begin with. We will want to use the Pythagorean identity, and what you said would work here. Let me show you something that actually will work a little bit faster. Okay? Rather than make this a 1 minus cosine squared, what I'm going to do is I'm going to take, notice how both of these have a b squared? I'm going to factor that out and look at what's left. See that? And that's 1. Now, it would end up getting, the things would end up canceling out so that we just ended up with a b squared if we did the 1 minus cosine squared, but this just kind of does it in one step. So that's 1. So notice here what we've got. I'm going to rearrange it a little bit. Putting the b squared after the a squared, it's a squared plus b squared minus 2 times a times b times the cosine of angle c. And that's going to equal c squared. And that right there is our law of cosines. Okay? Now, here's a question, okay? This is for triangles that are not right triangles, but it does work for right triangles as well. If angle C were 90, what's the cosine of 90 degrees?
0.
0, okay? So if this were a right triangle, I'd be left with just a squared plus b squared equals c squared. Okay? So, it'll work for right triangles, but it's not exactly efficient when you're using right triangles because we have faster ways of doing stuff. Okay? So, here is our law of cosines. I'll give it to you here. I want to point out a couple of things now that we've seen where this came from. I want you to notice a couple of things here. Notice that the side that ends up by itself over here is always going to be the side across from the angle that you're using. Okay? These will always be across from each other. Alright? And then the other two sides are used over here as well. Okay, so it's kind of like the Pythagorean theorem minus 2ab cosine of c. Alright? Now, there are two cases where we can use this. Alright? We saw different cases where we can use the law of sines. Angle, side, angle, 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 side, or the ambiguous case, side, side, angle, that we had to be careful about, but still worked. Okay? Here, we can use, if we know two sides and the angle between them, okay? Remember, side, side, angle was two sides and one of the angles across from one of the sides we knew. Okay? Here, the angle we know is between the two sides, or if you know all three sides. Okay? So, if you have side, angle, side, you can use the law of cosines to help you find the third side of your triangle. Okay? Because the side, angle, and side, the two sides would go in there for A and B. The angle is between those two sides. That would be here, and you would find the side across from the angle that you know. That third side. Okay? For side, 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 you would know C, A, B. You would have to find angle C. Okay, and as we'll see here in a moment, you're going to have to be careful about how you set it up to make sure that you're finding the angle that you actually want to find. Okay? And we'll look at some strategy there to help you with that. Okay? But first of all, let's start with the easier case. The easier case here is side, angle, side. Okay? So let's say, given side, angle, side, find the third side. So here's the formula as we've learned it. Okay? Here's what we're given. We're given angle A is 10 degrees, side B is 21, and side C is 15. Okay? We want to find what piece of information?
The third side.
Yeah, we're going to find that third side. We're going to find A. Now, here's the thing. The formula tells us we're solving for C. Does it matter? No, these letters are arbitrary, right? The key is, what angle do I know? Where is the side across from that? I know angle A. I'm going to be finding A. So instead of A's and B's over here, it's going to be B squared plus C squared minus 2 times B times C times the cosine of angle A. Alright? If you looked in your book, you'd have all three different possibilities. Solve for A squared, solve for B squared, solve for C squared. That's why I recommend learn the pattern and just recognize, hey, whatever the side is, it's got to be across from the angle. That'll help you set it up. Okay, rather than memorizing three of the same formula. Okay? So now we're going to plug stuff in. We want to look for A. B is 21, so I have 21 squared plus 15 squared, that's C squared, minus 2 times 21 times 15 times the cosine of 10 degrees. Cosine of 10 degrees. Okay? So now it's just a matter of being careful as we plug stuff into our calculator. Okay? Make sure you're in degrees. Hang on, 30 times 21. Yeah. Okay. And I don't know what the cosine of 10 is off the top of my head, so you guys can do the rest of it.
Yeah, minus.
Minus. Oh, yeah. Minus. Thanks. Okay.
666 is the 441 plus 225. Oh,
Never mind. Not much to do math.
Okay. So what do we end up with?
45.571156, but I didn't square root it yet.
Oh, you haven't square rooted it yet? So 45.17 and so on?
571.
571.
Yeah, and then square root is 6.751.
6.751.
Yeah, rounded.
Alright, so we'll give it to 2 decimal places like we have everything else. We're going to do everything to 2 decimals. Alright, so that'd be 6.75 at the end. Don't round till you get to the end. Alright, but we'll have 6.75. So, now I want you to think, we're not going to do the rest of this, but first of all, does our answer make sense?
Yeah.
How?
Because 10 is probably the smallest angle in that, so it would make sense that 6.75 would be the smallest side.
Okay, yeah, 10 is a really small angle. To get an angle smaller than 10 in a triangle is unlikely when you already have a 10 degree, so it makes sense that this is probably the shortest one. Also, what else?
When you add up each of the sides together, they're greater than the other ones.
Yeah, 15 plus 6.75 is bigger than 21, so I know that that makes sense as well. Okay? I would check, mentally check that stuff just to make sure at the end of each step. Okay?
Mr. Wilson?
Mm-hmm.
What if A was divided by 6? Would it work or not?
No, if A were exactly 6, you'd have B that's 21 units long. C would be 15 units long. And A would be exactly 6 units long. Stop. There we go. A would be exactly 6. These would be laying flat on top of the 21 if they were exactly 21.
So it has to be a little bit over.
It has to be greater than, yeah.
So it's not really.
Mhm. So, now, if we were going to go on and continue to solve this triangle, what would we use next?
Just like
Law of
solve
Cosines.
for
Law of Cosines.
We could use the law of sines. We could use the law of cosines now that we have all three sides. Or you could use the law of sines. One little tip though. If there's going to be an obtuse angle, which one would it be?
B.
B.
Which one would it be?
When I use the law of sines, the obtuse angles are the ones that can mess us up, right? So if I'm going to use the law of sines next, which angle should I get?
C.
C, because I know it's going to be an acute angle. And then I can just subtract to get what B is. Alright? See how this works together? And just paying attention to that ambiguous case as a possibility, we can come up with good strategies to avoid it. Alright? So I would use the law of sines to find angle C next, then subtract to figure out what B is. Okay? All right. Now, let's take a look at if we're given side, side, side. Okay? Here I'm given sides of 3, 6, and 8. And we just said if we're using the law of sines, we would leave that one that might be obtuse to the end, right? Do we have to worry about that when we're dealing with cosines? No, because remember, cosine's positive in the first quadrant, it's negative in the second quadrant. So you're always going to get the correct angle. There's no ambiguous case for the law of cosines. So that I can avoid it in the future, what could I find first? Yeah, I'm going to find angle C first. Okay? And that's the note I have here. When you're finding a side, go ahead and find the largest angle first, and that'll help you avoid any possibility of running into the ambiguous case later. Okay? So here, I'm going to find angle C, cosine of C. So as I'm setting this up, what needs to go by itself on the left-hand side of the equation?
8
The-
squared.
There you go, the 8 squared. It's always the side that's across from the angle you're looking for. Okay? So it's 8 squared equals 3 squared plus 6 squared minus 2 times 3 times 6 times the cosine of C. Okay? Don't be afraid to use your head here a little bit. You don't have to punch all that into your calculator. 64 equals 9 plus 36 minus 36 cosine of angle C.
The 36 is just 10?
Do they?
No, because
36
this.
cosine.
Yeah.
Gotcha.
Most common mistake students make. Most common. I'm sure you weren't the only one thinking it. All right?
No, I was testing you.
Yeah. All right. Don't forget this is 36 cosine. How do you solve these equations? You get the cosine by itself, then take inverse cosine. So this I can add.
That's right.
45 minus 36 cosine of C.
You can study the chemistry.
Okay. We subtract, we get 19 equals a negative 36 cosine of C, and that means cosine of C is a negative 19 over 36. For this, I've got to use my
Inverse.
calculator, use the inverse cosine. By the way, what do I know about the angle right here? It's going to be second quadrant because my cosine's negative. Alright, so listen, if we hadn't gotten this one first, we might have run into the ambiguous case later on.
How do we know if it's not in the second quadrant and not in the third?
Well, think about it.
Are they both getting?
Well, another thing. How do I know my angle in this triangle is
it's
not
less
a third quad?
Is it less than
Because
1?
for an, for an angle to be in the third quadrant would have to be more than 180.
Exactly, yeah. That's why we don't have to worry about it. That's a nice thing. It's okay. Alright. That's why we don't have to worry about it here because the other possibility is going to be bigger than 180 all by itself. And we know all the angles in the triangle only add up to 180, so that's not going to be possible. So what do we get here actually?
121.86.
121.86? Okay, good. Alright. And that's obtuse, that's fine. Now we could use the law of sines to find one of our other two angles and then subtract to get the last angle. Okay? Alright, any questions? Not a terribly difficult formula to use. You just have to be careful with it. Okay? Take some time to memorize it, and then be careful with it. Okay? Alright, one last thing here that I want to look at today, and I promised that we would be looking at this, and that is another area formula. Okay? Now, if we have side angle side, we already have a formula for that, right? The area equals what? Remember our formula for area?
Is it 1/2 base of height?
Well, that's
No,
for
because
any
it had
triangle, but we didn't know the height. It was 1/2.
1/2 B, or no,
Okay, is it
Oh, I saw it.
1/2
Yeah, it was
BC
like
it's like 1/2 BC
1/2
sine
1/2 BC sine A. Or
1/2 BC sine A or 1/2 AB sine of angle C. Yeah.
Two sides and the sine of the third.
Yeah, the sine of the angle between them. Okay, so if you're given side angle side, like in this case, I would, if I wanted the area of this triangle, I'd just do 1/2 times 21 times 15 times the sine of 10. Okay.
1/2 times the 3 things you know.
Yeah, for side angle side. For side, it's a little different, okay? Here's our formula for side. It's called Heron's formula, okay? Or depending on the book you read, they might call it Hero's formula, all right? I've seen it with both. But here's the formula, and it's actually, it looks harder to remember than it is, okay? The area is the square root of S times S minus A times S minus B times S minus C. The key here is remembering what S is. It's what's known as the semi-perimeter, or half of the perimeter. Okay? The prefix semi means half. Alright, we saw earlier when we did exponential functions, when we looked at our compound interest, semi-annually was every half of a year. Okay? Semi-perimeter means half of the perimeter. So the perimeter is the 3 sides added together, A plus B plus C, and we're dividing it by 2. Okay? So, here I'm looking for the area of this triangle, and my semi-perimeter is going to be 8 plus 6 plus 3 over 2. So that's 17 divided by 2 is 8.5. Okay? So there's our semi-perimeter, 8.5. Now, for our formula, the area, watch how we set this up. The area is going to be, you need a big old square root, and then you just take the 8.5 times 8.5 minus each side. Okay? So it's 8.5 minus each side. So my sides are 8, 6, and 3. Okay? So now I have the square root of, and listen, this is where, again, don't overuse your calculator. Think. You can do this subtraction in your head. It's not difficult. 8.5 times 1/2 times 2.5 times 5.5. Okay? Make sure all of this ends up under the radical. Okay? And what do we get?
7.64
7.64?
units squared.
Okay. Is that correct? What you guys got? Okay. Let's double check that. We got this angle here to be 121.86. The area would be 1/2 times 6 times 3 times the sine of 121.86, right? So punch that in. What do you get?
7.64.
7.64. Hey, what do you know? Okay? So we got the same thing. In this case, we didn't need to find any extra information. Okay? Here we had to use the law of cosines to get an angle first, then we could use the SAS area formula. Okay? So, do we have to have both area formulas? No, if we have our other trig. But is it useful sometimes? Yeah. Okay, it can save us from having to do other work. Heron developed another area formula for quadrilaterals that was built almost exactly like this, except it was times s minus d for the fourth side. The thing is, it only worked if you had a quadrilateral that was inscribed in a circle. Okay? It had to be inscribed in a circle. Because that's how we derived this formula. It's based on things being inscribed in a circle. So it only worked in that case, but it was still cool nonetheless. So, okay. So that's everything. Okay. I give you an example here. You could take a look at here later. Notice this one I could not inscribe in a circle, you know. I could get 3 of the corners in a circle, but not the 4th one. So if we were finding the area of that, we'd have to cut it in half. Okay? We'd have to cut it in half, either that way and then use a bunch of trig, or cut it that way and use a bunch of trig. Okay? You can take a look at that later if you want. That's kind of a fun thing to try. Alright, see you guys. Have a great day.